Alright, so I'm going to go over how to do all of these problems. Hopefully the shadow is not too bad, you can actually see here. So the first one, on these when you're trying to figure out which one's the derivative, which one's, one's position, one's velocity, one's acceleration, so you're just trying to figure out which ones are the derivatives of each other. So you can either just like pick one and think about it, or the easiest way is to look at when the slopes are zeros, because remember, derivatives are just slopes. So I can see slopes of 0 here and here on C, and then on A I got a slope of 0 right here. So all you got to do then is, like, let's say I start with A. I know right there the slope is 0. Well, so at that same value of time, the derivative of that should hit 0. So obviously B is the derivative of A. And then going backwards on this one, you see right here, the slope is 0 here. So in that one, whatever one is the derivative of C should cross 0 right here, right in this same line. I guess that should line up perfectly. I don't know that it does. I guess it kind of does. So yeah, right there the slope is 0, and that hits 0. Right there the slope is 0, and that hits 0. So then you know C is position, the derivative of that is A, that'd be your velocity, and the derivative of that is B. So I guess to write that down, I would write, let's see, the position function is C, the velocity function is what did I just say? A, and the acceleration is B. The other way you could have done it is just pick one and just kind of think about slopes. Like, oh, I picked this one. It starts off positive, and then it goes closer to 0, hits 0, then it gets negative. So that's just following that parabola. But I think that was harder. Using the zeros is... Okay, so I was just talking away there, going over problems until I realized the iPad had stopped recording because it ran out of memory. So, let's see, I went through a whole bunch of stuff. Luckily I didn't get too far before I noticed it, but so I think it shut off like right when I switched to this one anyway, so it's not bad. It was a good switch there. So this one was quite a bit harder than this one. This one, the whole idea of using where the slope is 0, it works. So if you didn't think of that before and you didn't do this problem, you should probably pause this video and try that on this one now. But if you did think about it, or maybe you thought about it just with slopes, so if we just work our way through these, like start with A, B, C. So like, well, we'll just start with A. The slope is 0 right here at the beginning. Well, so then you might think B is the derivative of A, because boom, it starts at 0. Problem with that is you can't just use 0. You should kind of look at it more than that. This one starts with a slope of 0, but then the slope becomes positive and continues to get more and more positive as you move along. B doesn't work because it starts at 0 and goes negative. So B is definitely not the derivative of A. But you might also notice C also has the derivative at 0 right here at the beginning. Starts at 0 and then gets negative. So there it is. This starts at 0 and gets negative. B is actually the derivative of C. And then if you look at B, the slope or the derivative is 0 right here. A hits 0 right here. To the left, B has a negative slope. To the left, that's negative. To the right of that point, B has a positive slope. To the right, that's positive. So A is the derivative of B. So it goes C, then B, then A. So B is the derivative of C, A is the derivative of B. So that's position, velocity, and then acceleration. And I wrote that there. Position C, velocity is B, acceleration is A. And here are actually just the answers for the even numbers. So if you want to just check your answers, you can go ahead and pause this right now, and there's just answers. I didn't just write the answers for the odds because you have them. You can check in the back of your book. So there are just the answers. And I'm going to go on and just actually do every problem and explain every one beyond that. So 34, we'll go ahead if you didn't get that. And I'll go over 37 and all the odds too. Again, since I already did some of it, that was stupid. So 34 is the balloon one. It tells you the volume of a balloon, or of a sphere. You know, that's the volume. That's just the formula for the volume of a sphere. So it's 4/3 pi r cubed. Yeah, you knew that. Good job. It's 8th grade standard? Oops. Got the peanut gallery back there. Whoops. I think. There we go. Accidentally shut the iPad off. Okay, so it tells you the volume. AS, at what rate does the volume change with respect to the radius when r equals 2 feet? So here's your balloon, here's your radius. Obviously, as the radius gets bigger and bigger and bigger, the volume will get bigger. On A, you might be tempted to plug in 2 for r, because it asks when the radius is 2 feet, but that's not what they're asking. That would give you the volume, give you the actual volume when the radius was 2 feet. But that's not what we want to know. We want to know at the rate at which the volume is changing with respect to the radius when r is 2 feet. Whenever you hear at what rate does something change, you should be thinking of derivative. So we need to find the derivative of this. If we do the dv with respect to r, derivative of volume with respect, that's going to tell you it's the rate the volume changes as the radius changes. So we do the derivative of this. It's easy. That's just a constant. That's a constant. There's our variable that we're doing the derivative with respect to. So you just do power rule, right? Those are just numbers. So we just drop the 3 down. 3 times all of this. Right? Well, 3 times, it'd be, show my work over here. 3 times 4/3 pi, and then you have r, and you subtract 1 right there, right? So 2. Well, 3 times 4/3 is just 4. So really you have 4 pi r squared. So that's how the volume changes with respect to the radius. Now you plug in 2. So it would be 4 pi times 2 squared. 2 squared is 4. So you get 16 pi. And the units on that are actually feet cubed per foot, which is weird, because you might want to simplify that and say feet squared, but that's not true. It's the volume changes by top number's volume. So for each foot, the radius is changing by, the volume changes by 16 pi cubic feet. Yeah, don't worry about that. But that's how you would do that problem. B just asked, by approximately how much does the volume increase when the radius changes from 2 feet to 2.2 feet? That is just plugging it in. Find the volume here, find the volume here, calculate the change in volume. So V of 2 is 4/3 times pi times 2 cubed. V of 2.2 is 4/3 times pi times 2.2 cubed. Calculate those out, which I don't feel like doing, but I need to. Probably some weird noise going on in the background. Suctioning drool out of Barrett's mouth. So let's see. Okay, that'd be 32/3 times pi. This one's 33.51. What's that? 2.2 cubed. 44.60. So it goes up from that to that, so you subtract those, and your change in volume will be 11.09 cubic feet. That's how you do that one. Okay, I had to stop filming in the hospital because it was getting too loud and too distracting. So, especially for this problem, it's a long one. It's more difficult than one I'll probably give you on your quiz. So let's see here. So it tells you that you got a particle moving along the line y equals 2. I already drew the line y equals 2, so you can just imagine there's a dot on there moving left and right. And they give you the position function 2t to the third minus 13t squared plus 22t minus 5. A is the good old describe the motion for t is greater than or equal to 0. Okay, there's a couple different ways you could do this. You could graph the position function. You could graph that. That would be a good way to do it. Maybe start there. You can get the velocity function, and that'll help you figure out when velocity is positive, moves to the right. When velocity is negative, moves to the left. You can also see when it hits 0 for when it turns around. Really, we just kind of want to use all of these things together. I won't give you that question on a quiz. We'll be more specific. Like I'll say, when does it move to the right or something like that. But so to answer this question, let's see. I'll just graph that, see what happens. Okay, this is position. So it tells me it's going to start off negative. So it's going to start somewhere over here, and it's going to move to the right, keep moving to the right until here, and then it's going to start moving left. Whoops, there we go. Start moving left, and then move back right forever. So if I want to figure out where it starts, like I just put the dot there, I don't know if that's where it starts. So if I plugged in 0 for t, 0, 0, 0, I'd have negative 5. So x 0 equals negative 5. That means this thing's going to start at negative 5. So we could say starts at x equals negative 5, then moves, I think it goes, right? This is going to start down here at negative 5, and now it looks like it's moving to the right because it's getting more and more positive. Then moves right. Right here is where it's going to turn around and start moving left. So you can find that point on your calculator by doing the old calc button, and then do maximum and go to the left. You just want the highest point, like right there in that little region. So you put it to the left of it, put it to the right of it, and then guess right there. So it looks like 1.15 seconds. It'll go to 6.14 on the x-axis. Remember, these values are the x values, and on this x-axis, that's time. So that's one way to do it. Or we could have used our velocity. I like using the velocity function. So write the derivative of that. So we'll go v of t. What do we have? 6t squared minus 26t plus 22. Go ahead and take a look at that here. 6. I don't want to see the position one. I don't want to get confused, so I'll turn it off. Remember, unhighlight the equal sign. I don't want to clear it though, because I might go back to it later. So there's my velocity function, and just as I predicted right at the beginning, velocity is positive, so it's moving to the right. Then right there, velocity is going to switch to negative, and that's when it's going to start moving to the left. And you can see if you look at them both at the same time. So as soon as this velocity curve crosses the x-axis, crosses 0 right here, that's when velocity switches from positive to negative. So that's when the thing turns around. Well, notice on the position curve, it's getting more and more positive, so it's moving to the right, and then right there it moves to the left. Those line up. It's not a coincidence. Alright, because this one's the derivative of this. When the derivative hits 0, that hits 0, right? It all makes sense. So you can use either one to figure out your times for when this thing turns around. like I just showed you, you could have done the maximum thing right there, or you could use your velocity equation and calculate the zero, right? That's when the velocity hits zero. If that was easily factorable, you could factor it, set it equal to zero, factor it. That does the same thing for you. So let's just go ahead and, I forget what the number was. So I'll calculate the zero. I should get the exact same thing as I got before. There's to the left, to the right. Guess 1.15. So it starts at x equals -5, then moves right until t, oh, we'll say moves right. I don't know how to write this. It's moving right from 0 to 1.15 seconds. Then moves left. We could figure out the point it stops and turns around. I don't know if we need that. Who cares? Then it's going to move left this whole time, right? Velocity is negative until right there. It's going to hit 0 again, and the velocity is going to become positive again. So let's figure out what that point is. This looks like 3.18. So it moves left from 1.15 to 3.18. And notice these are all just, they don't have the equal to, because at 0 seconds it's not moving. At exactly 1.15, well, I rounded, but it wouldn't be moving. That's when it turns around. So it moves left from there, and then it moves right for the rest of the time. For t is greater than 3.18 seconds. So it just keeps moving right forever after that. So that's A. We could get more detailed if we wanted. I don't know what the back of the book says. I haven't looked. B, let's see, when does the particle speed up and slow down? Okay, this is like probably the hardest question of the whole thing. And this, I said that video where I'm pushing my wife around in the hallway wouldn't come into play until chapter 5, but this is actually, you need to know that for this part B. It gets tricky. So I'll do this and I'll explain it, but it's not going to be on this quiz for 3.4. So maybe it does show up here. Maybe it will be on your test for this chapter. I don't know. So speeding up and slowing down, you got to think about acceleration, right? If that's what speeding up and slowing down is. If you have a positive velocity, so you're moving to the right, and then you have a positive acceleration, it's pushing it even faster, it's going to speed up, right? It's not as simple as saying positive acceleration means you're speeding up, negative acceleration means you're slowing down. It doesn't work that way. Because of that whole idea of, if you've got a thing that's moving to the right and you have a positive acceleration, yeah, it's going to speed up, it's going to go faster. It's like my wife was moving this way and I pushed her from behind, we go faster. But if your object is moving to the left, so if she's going to the left and I have a positive acceleration, I'm pushing against her, we're going to slow down. So it depends on which way you're traveling and what the sign of your acceleration is. So to speed up, you need to have velocity and acceleration have the same sign. This is almost like notes inside of a problem. So right, if you go in positive velocity and you have a positive acceleration, you're going to speed up. If you have a negative velocity and then a negative acceleration, it's going to speed up in the negative direction. That's still called speeding up. Right? Your speed, your absolute value of your velocity, your speed's going to increase. It's just the speed increases this way. Slow down. You got velocity and acceleration have different signs. So, if velocity is positive, you're moving to the right, and then your acceleration's negative, it's this way, different signs, it's going to make that thing slow down. Or the opposite, if the velocity is negative and the thing's moving this way, and your acceleration is positive, different sign, it's going to make that thing slow down. It's not going to go as fast. So to actually do this, you got to check a lot of stuff here. Easy way to do this is kind of make a little chart. I'm trying to move my paper. Let's see, what do we know? We know which way it's moving, right? We know where the velocity is positive and where the velocity is negative. Didn't we figure that out? Here's my velocity equation. I know from 0 to 1 point whatever, 1.5. Let's make a little chart. From 0 to 1.15, my velocity is positive. So I'll just make a little from 0 to 1.15, velocity is positive. I need to know what the acceleration is at in that region. So I can get my acceleration function. Just derivative of that. Acceleration is 12t minus 26. Okay, so we can go ahead and graph that. 12x minus 26. Okay. It's negative from 0 to right there, 2 point something looks like, and then positive after that. So let's calculate that. I don't need to use a calculator, that's an easy one. Set it equal to 0, so 0 equals 12t minus 26, add 26, divide by 12. So t equals 26 divided by 12. I think that was faster than doing calc. I don't know. 2.17, 167, who cares? 2.17 seconds. So that's like our key point in our acceleration. So I'll make myself a little note here. Acceleration. Let's see, here's 0, here's 2.17, and then here's the rest. Let's see, it went from negative to positive. So from 0 to 2.17, my acceleration is negative. So that tells me between 0 and 1.15, acceleration is negative. Now here's the thing. Since let's put both of these on the same graph, velocity and acceleration. Right here, since acceleration changes sign, we have to include that as a key point. Velocity changed from positive to negative over here, and it stays negative this whole time, but notice the velocity is getting more and more negative right here. That basically means it's speeding up, right? And then right here the velocity is still negative, but it's getting less and less negative, so it's slowing down. So this whole region right here, as far as velocity goes, it's still moving to the left, but here it's getting more and more, it's going faster and faster to the left, and then right here it's still going to the left, but now it's just slowing down. So that's going to change everything, and we can see that because our acceleration changes signs. So we're going to go to 2.17 seconds. So from 1.15 to 2.17, what happens? Well, that's from here to here. We know our velocity is negative this whole time. And we know our acceleration is negative because it's over there. So just making a little sign chart here. Then we're going to go from 2.17 to our next sign change, which for velocity was 3.18 seconds. So from 2.17, so from here to here, our velocity is still negative, but now our acceleration is positive. And then our last one is for everything bigger than 3.18 seconds. And for this, we have both positive acceleration and positive velocity. So now we can tell where it's speeding up and slowing down. Different signs, so velocity is positive, acceleration is negative, meaning the thing's moving this way, but the acceleration is forcing it this way, so it's getting slower and slower and slower. So that's slowing down. Same sign, so velocity is negative, it's going to the left, and the acceleration is pushing behind it to the left, it's going faster and faster, that's speeding up. And then here again, different signs, that's slowing down. And that's, if they're both positive, that'll be speeding up. So we could write this in summary. It's slowing down. Let's see, how do I want to write this? I can write it as intervals, or we can do it like this. Doesn't matter. Slowing down from 0 to 1.15 and from 2.17 to 3.18. Speeding up from 1.15 to 2.17 and from 3.18 to infinity. So there's that. That's like I said, that's not going to be on your first quiz. But there it is. There's an example of what's to come. So going to part C. Pretty much now we should be able to answer all of the questions, I think, just off the work we've done already. C, when does the particle change direction? Well, we've got our nice little chart here. Velocity changes from positive to negative at 1.15 and negative to positive at 3.18. So we've already answered that question. Or we answered it up here even when we described the motion. Alright. So now we got it down now. That's at 1.15 and 3.18. I think that's what it was. Yeah. When is the particle at rest? The rest of these are easy now. It's at rest when velocity equals 0. Hey, that's when it's turning around. So it's at rest at those same answers. Because when it changes directions, that's when it's at rest, just for an instant. E, describe, it's kind of becoming redundant now. It's saying describe the velocity and speed. We just did all that right here. Don't need to do it again. We could put it into words, but I'm not worried about it. Velocity starts positive, goes negative. Yeah, we kind of covered everything. Let's answer F though. S, when is it at 5.2? So anytime it asks when, you're going to be solving for t. Now you just got to decide are you going to use your position function or your velocity function. Like if you do 5.2, well, they told us it moves along the line y equals 2. So we just got to know basically when does x equal 5. Right? Because it's always going to be, the y value will always be 2 if we're moving along that line. So when does x equal 5? Probably going to go back, use the position function, plug 5 in on that side, and solve it. So, let's see. Instead of flipping back and forth, 2t to the third minus 13t squared plus 22t minus 5. When is that going to equal 5? And you might want to, or you might not know how to solve that. You can subtract. The best way to do it, just use your calculator. Subtract 5 from both sides. So you got that whole thing. Minus 10 equals 0. And now solve that for t, which you can use your calculator for, right? Since it's equal to 0, just graph that and find the zeros. So if we graph it, I'll shut those off. And I'll just edit my old one to say, I can't get to it. -10. So it's going to hit it 3 different times. And that makes sense that it hits it at 3 different times. Because remember, this thing's moving back and forth. Right? It started off to the right, then went left, stayed left, then went back to the right. So it started off to the right, it's going to go past 5, and then goes back left, past 5, and then goes back right, past 5 again. So it hits it 3 different times. And if we just calc the zeros of all these, we'll get the 3 different times. Which, for the sake of shortness of the video, I don't think I'm going to do. You can sit there, calc all 3 of those, and you'll get the answers they give you in the back of the book. You'll get 3 answers. I don't know what they are. That's how you do it. Okay, 40. Pen's running out. I think it was 40, right? 40 says the speed of a particle at t equals a is given by the value of the velocity at t equals a. That's false. Speed and velocity are not always the same. Velocity has direction. You can have a negative velocity. You can have... Bless you. You can have negative velocity, so you can have a thing moving to the left at 5 meters per second. So that would be negative 5 meters per second on velocity. The speed would still be known as 5 meters per second. So that's why I wrote in the answers. Velocity could be negative. Speed is the absolute value of velocity. Speed doesn't have direction. So that's that one. 41. The acceleration of a particle is the second derivative of the position function. That's true. Hope I'm right. I didn't look these up in the back. True, right? You have your position function, take the derivative, you get velocity. Take the derivative again, you get your acceleration function. That's pretty much all there is to that. So that's true. 42. Let's see. Find the instantaneous rate of change, and they give you a function at x equals -1. Well, an instantaneous rate of change is just the derivative at x equals -1. So we just got to find the derivative of that. So we got f of x equals x squared minus 2 over x plus 4. So to do the derivative of that, this part might throw you off. It's easiest if you change it to a power. So instead of 2 over x, that would be 2 times x to the -1. Now you can do the derivative of that. If you never thought of that before, you might want to try that. So, oops, so now do the derivative, f prime of x will equal, let's see, 2x. Remember, power rule, this number times this, so -1 times -2 is plus 2x, and then subtract 1 from the power. So I have 2x plus 2x to the -2nd power. And if we want the instantaneous rate of change at x equals -1, I just do f prime of -1. So I plug in -1. It might be easier to write this like so instead of x to the -2 power now, you might want to switch it back to 2 over x squared, right? Negative power, move it to the bottom. So I have 2 over -1 squared. So 2 times -1 is -2. -1 squared is 1, so that's 2 over 1, which is just 2, so I have -2 plus 2. That's how you get 0. So that gives you your answer of C. '43. Find the instantaneous rate of change of the volume of a cube with respect to side length x. Okay. You gotta remember how to find the volume of a cube. By definition, a cube is all the sides are the same. So x, x, and x. So the volume of a cube, you just multiply length times width times the depth or the height, however you want to say it. So the volume of a cube is x to the third. If you didn't realize that, you can probably finish the problem now. So find the instantaneous rate of change of the volume. Oh, so do the derivative of this function with respect to the side length x. So dv dx, it's just 3x squared. And that's your answer, D. Okay, 44. They give us a position function, and we gotta figure out when it's moving to the left. So S of t equals 2 plus 7t minus t squared. At which of the following times is the particle moving to the left? So to me, moving to the left means velocity is negative. So I'm trying to figure out when is the velocity of that going to be negative. So it's easiest probably just to find the velocity function, which derivative of that, 0, so I'd have 7 minus 2t. Alright, power rule, 7 minus 2t. So when is that going to be negative? Well, there's a very easy mathematical way of doing that. Just say the hat has to be less than 0 and solve that inequality. Or you could set it equal to 0, and that would tell you when it hits 0, and then figure out on one side is it positive or negative, and then on the other side is it positive or negative. But that's easier. So just subtract 7, so negative 2t is less than negative 7, divide by negative 2. Remember, when you divide by a negative in an inequality, flip it. So when t is bigger than 7/2, or when t is over 3.5 seconds, that tells me at 3.5 seconds the velocity of this is going to be equal to 0. So if you think, here's 3.5 seconds. Over here my velocity will be positive. Over here my velocity will be negative, and it's going to go through that. So, oops, that's that way. Whatever. So to answer the question, at which of the following times is it moving to the left? Well, the answer better be above 3.5 seconds. So it can't be 0, it can't be 1, 2, can't be 3.5, it's got to be 4, E. Because at 3.5 is when it would equal 0, after 3.5 is when it's less than 0. The velocity. When is the particle at rest? Well, we just figured that out. If you just change that into an equal sign, you get t equals 7/2, right? That's when velocity does equal 0. So that's how you get C for 45. Okay, that was very long, but hopefully that made sense.